I want to talk about model-based controller design methods. By first starting to talk about what we mean when we talk about model-based design. Whenever you have solved an engineering problem using formulae, you've been using models. So let's say you're designing a heat exchanger and you have a duty given by formula like this. If we're trying to find out the duty, this is the natural direction for this equation. In other words, we start with known values for u, a, and delta t, and we calculate the duty. So this is known as the rating problem, but this is based on a certain model of how heat is transferred. In some cases, we'll be using the opposite direction. We'll be taking a given Q, so we'll start with Q, we'll know U and delta T, and our target will be to calculate A. And to do this, we will solve the equation, right? So we will rewrite the equation to be in terms of A. And now we will have a different equation. And what we've done here is we've now solved a design problem, because the other specifications, the Q and the U and the delta T, are typically not within our control, but we can choose an A. And so we've gone from just looking at a heat exchanger which is standing there with known values to determining the required area for a new heat exchanger. Now, to place that into control terms, we also have a natural forward direction. If we have a transfer function with a known input, and we are trying to figure out what the output is, and often our input took the form of a step input, but we had a known U, a known G, and we were trying to calculate Y. And this would be the forward or simulation direction. Now, if we are solving in the opposite direction, so in other words, what happens if I want a certain Y? Let's say I want a transfer function with a certain time constant. Now I can calculate G, and this would be the design problem. So given some desired relationship behavior, how can I calculate G? Now the process is very similar in calculating the desired G as it was when we were calculating the desired A. We rewrite the equation. So we interpret this block diagram over here as equivalent to this equation, and therefore if we're calculating G, we can isolate G as Y over U. And so this way, if we have a known Y and we have a known U, we can calculate G. Of course, our problems aren't always as simple as that, because sometimes G is itself made up out of other blocks. So it may be that the overall behavior we could call G, and this would be the relationship between U and Y. But we can imagine an arbitrarily complex connection of different blocks all being put together in order to obtain that overall behavior. And so I could have an A and a B over here, and perhaps this part is within my control, and I want to know what A is. Now, this is actually the basis of direct synthesis model-based controller design. Now we are ready to consider the controller design problem. And here we will assume that all of these transfer functions are known. So we'll know everything about the system itself, but our job is going to be to figure out what controller we need in order to obtain a desired closed loop behavior. And what that means is if I put a step into the set point and I would like for a first order transfer function with a time constant of tau c as the output y, right? Then what should GC be? So this is a lot the same as the previous design problem, right? We've got a number of known values. All of these things are known, and we're trying to figure out an unknown. And again, we have an equation. We know that the closed loop transfer function y over ysp is going to be all of these forward parts, all of this divided by 1 plus everything in the feedback loop according to our feedback rule. So that's going to be Km times Gc times Gv times Gp all over 1 plus Gc Gv Gp Gm. So this is our known closed loop transfer function. And again, in the math, this is going to be known. And all of these things are going to be known. But we want to work out GC. And so it's a slightly more complicated formula, but the math, the basic idea is exactly the same as before in the other design problem. Now, we can make the math a little bit easier if we simplify these equations a little bit. So we'll take all of the forward part of the functions inside the loop to be equal to g. Now what that means is all of this, right? We'll call that g. And similarly, we will take this Km along with GV there, and we will also pretend that that is also equal to G. Now in the book, that effectively means that we have to assume that Km is equal to Gm. So that just means we assume similar dynamics in that transfer function. Now you'll see that that simplifies this equation down to y over y sp is equal to gcg over 1 plus gcg. Now for me that is actually equivalent, if you think about it, to changing our block diagram so that it is now this much simpler block diagram where which you've seen me draw in the class, where we've bundled all of the system dynamics into one G, and we now have this very simple block diagram where we don't have to worry about all these other things. We just say we have a known G, so G is known, and we're trying to figure out GC given a known closed loop behavior, so that would be tau c. And so this is kind of the first steps. We're going from this really complicated block diagram over here. We could have done all this math, right? We could have just calculated everything and we could have plugged in all of this stuff there, but we simplify our math considerably if we reduce it down to this simple block diagram situation that we have over here. So another distinction that we'll be making is the idea that we'll be distinguishing between G, this G, in the actual process, and we'll be distinguishing between G, which we will say G is the actual process itself, right? The tank or whatever, and this is G. But we don't in general have access to the real process, itself while we are doing calculations. What we rather have is a set of equations which describe G. And so we have a model, and our model perhaps takes a particular transfer function form. And that's going to be called G tilde, or the actual model. And so in terms of our design calculations, we can, the reason why we make this distinction is because we can find the forward relationship with the real plant by doing a test. So we can go onto the plant and we can introduce some test and we can actually observe what happens, right? And so that's always available to us. But in real life, the real life plant does not allow us to do math on the real life plant. It only allows us to do this this kind of forward direction calculation. But the model that we have, the model takes the form of mathematics, and that allows us to plug it into formulae. And so by and large, when we write the formula for equations that involve the real plant, we'll only use G if it is available in the forward direction. But we'll use G tilde whenever we're doing math and doing rearrangement kind of calculations with G. And so we distinguish between the model and the plant. And later we'll also be looking at this idea that there may actually be a mismatch called the model-plant mismatch between this ideal model, which we've perhaps linearized, we've perhaps simplified so that it's of lower order, and the true behavior, which is now the real actual plant. So actually, if we go back to our equation here, this equation is in let's say the forward direction, right? Because this is the kind of predictive behavior that we would be able to get from the actual plant. But our next step is going to be to solve for GC, right? And so if we solve for GC in that equation, what results is GC equal to y over ysp over 1 minus y over ysp, all with a inverse of the model in front of it. So this is effectively the design equation that we will use. This is the basis of the direct synthesis method. So once we've derived this formula, we can just choose ysp. We can know from testing or whatever what y tilde is, and we can plug it into this formula and we can calculate GC. And once we've actually written out that formula in this form, we have completed the direct synthesis technique. From this point on, it's just math to actually find GC. So just before I said that we may want to just use a first order desired output. So we may call this what we actually want. We can kind of distinguish between the real one, which will actually happen, and what we want to happen by subscripting this D, so that we say that we have a desired output. And remember that actually this whole box, everything inside this box, is itself just a transfer function. So the closed loop transfer function that we have over here is just the relationship between the input and the output. And so desired, one of the things that we would like to have perhaps is a output which simply moves directly to a new set point. So if a set point is there, that we want a nice first order response with a simple time constant. So that may be an easy thing that we want, and we know the transfer function of that, the overall transfer function of something like that would be tau cs 1 over tau cs plus 1. Okay, so that would be the transfer function. And if we plug this in to y over y sp d, right? If we say that, so that is the desired output, and we just take that and we substitute it into there, and then solve for GC, we end up with GC is equal to 1 over G tilde 1 over tau CS. So this will always happen, and in now you can kind of spot the problem here, that sometimes G tilde itself, once we've inverted G tilde, we may have a physically unrealizable G, GC. So if you think about what G tilde could possibly be, perhaps G tilde is something like, let's say G tilde is S plus 1, and it's a high order transfer function with lots and lots of brackets under the line. Now when we plug that into there, there's going to be 1, 2, 3 orders above the line and only 2 orders below the line. So this GC will not be physically realizable. So that's one of the problems with this kind of technique. In that case, we will not in fact obtain the exact output that we desire, because we can't actually build this GC. It's not possible. It's not physically realizable. Another issue is, what if our process actually contains some dead time? That means by the time we invert, we will require looking into the future, because we'll have this positive dead time. So in practice, if we see one of these here, we have to take that into account in the original desired output. We have to say, well, we have to live with that delay. We cannot remove the delay by incorporating control. So we'll have to accommodate the delay in our desired output, and so that makes our life a little bit more difficult. We'll end up with a slightly different equation now. So we'll end up with GC is equal to 1 over G tilde with some dead time, e to the minus theta s over tau cs plus 1 minus e to the minus theta s. And we have another problem that so we've removed the problem of having these positive dead times in the inverse by accommodating that in our desired output, but we haven't removed the problem of being able to calculate this transfer function. And one of the ways in which we will use the model-based design techniques that we're talking about now is we'll say, in fact, we cannot just build this controller, this exact same controller, because it's far easier for us to buy an off-the-shelf PID controller, right? So in practical cases, GC will actually be equal to KC 1 plus 1 over tau IS plus tau DS. Or in other words, the ideal PID controller, right? So one of the ways in which we'll use the direct synthesis technique is let's say the straightforward way is to calculate this and then simulate GC or implement something, build a controller that is exactly like this. A more practical way is to say, I have one of these, now I just need to figure out the parameters which will match GC, this PID controller, closely to this relationship over here. Now, you can see that this equation doesn't feature any e's, right? There's no e's in here. If G tilde originally contained dead time, then that dead time will cancel with the dead time that we have in the controller. So by the time we substitute this into there, this dead time will be below the line, and that dead time will be above the line, and it will cancel out. But this dead time will still remain. And if we're trying to approximate these two by one another, in other words, if we're trying to approximate this big difficult controller with a simple off-the-shelf PID controller, we'll have to get rid of this dead time. And depending on the order of the controller, we'll typically multiply it out, and then we'll do substitution. We'll do some kind of a simplification or an approximation of E, and we'll only really bother with this E, the one in the numerator. And so how that basically plays out is for the simple case of a first order plus dead time model, we can do the substitution, which is a first order Taylor substitution, which is 1 minus theta s, which is approximated by 1 minus theta s. So you can go and verify for yourself that this is the constant term, so this is the term with s equals 0, and this is the first derivative term. And so we'll plug this into we'll plug this approximation into there, and by the time we're done, we'll have a purely rational function which is the same order as the PID controller, and we'll then calculate the coefficients by matching coefficients. So we'll calculate these controller parameters by matching coefficients, and you can go onto GitHub and see how I've done that using SymPy.